Hello everyone, my name is Hampus Monefjord. I'm a PhD candidate from Lund University in Sweden, and this is my presentation on the workshop on low-cost spectroscopy techniques for mosquito surveillance, which is hosted by the University of Cape Coast in Ghana. My team consists of Associate Professor Mikkel Buregård, myself, and PhD candidate Meng Li. This part of the presentation, I will cover an instrument which is called biospace. I will talk about some potential mosquito applications you could do with biospace, and I will finish with a potential upgrade for the biospace. Biospace stands for biophotonics, imaging, optical, spectral, polarimetric, angular, compact equipment. The idea is that you have a sample and then you want to acquire a lot of different information from your sample. You have the spatial domain where you do imaging and you can also spin your sample around. You have the spectral domain where you basically get the spectrum of your sample for different regions of it. You have the polarimetric domain where you can find the degree of linear polarization, again for different parts of your sample. And you have the goniometric domain where you can get the scatter angle of your sample. Some of its main benefits are its versatility. It's measuring all of these different domains as mentioned, acquiring a lot of data on your sample. Then it's rather cheap compared to other instruments. It costs around 3,000 euros or 30,000 CDs, and it's very reproducible as we have shared the part list and assembly instructions. Right now there is one biospace in Ghana at UCC. There is one in Côte d'Ivoire. There is also one in Ecuador and 3 in Sweden. It's also lightweight and portable. We can bring it out into the jungle or to a classroom or wherever we need. And finally, it's modifiable. If you want to change a little component, it's very easy. You can just 3D print another part or just reassemble the Lego slightly. I will now cover how we acquire this information from the different measuring domains. The spatial domain we get by imaging our sample and rotating it in 2 different angles. This angle we call the yaw angle, and you can see an example of a bark beetle which is rotated in this angle and its corresponding polar plot. The other angle we call the aspect angle, and combined we can get the full 3-dimensional information of the sample. The polarimetric information we get by illuminating our sample with linearly polarized light. Then we have an analyzer which is rotated into different positions, capturing copolarized and depolarized light. Here you can see the bark beetle being illuminated with copolarized and depolarized light respectively. So in the top you can see flashes all over the body, and you can see these soap bubbly colors in the insect's wings. In the bottom you don't see these flashes, and you can also see that the most intensity is acquired from the bulk of the insect's body. You see that it looks like it's almost glowing. This is because the photons have scattered around inside the body and thereby lost its polarization. The goniometric information is acquired by rotating the light source around the sample and acquiring images. You have a polar plot of this scatter angles intensity to the right. The spectral information is achieved through LED multiplexing. Here we illuminate the sample by one wavelength at a time, and we acquire an image. Then we go to the next wavelength, acquire another image, and so on. We have 8 different wavelengths in biospace, ranging from 365 nanometers to 940 nanometers. We acquire one image where no LED is on to do background subtraction. This way, we create a spectrum with 8 points, from ultraviolet to near infrared. All in all, the biospace has the potential to acquire an enormous amount of information. We have 8 spectral bands, 67 scattering lobes, 4 polarimetric parameters, 45 yaw lobes, and 180 roll lobes. This results in over 17 million unique images of a single sample. This is a lot of information, so usually you would tailor your experiment to only capture what you need. Now I will talk about what mosquito measurements we can do with biospace. So far, we haven't published any studies containing biospace mosquito measurements, but I have prepared some figures just briefly for this conference. In a field campaign in the Tai rainforest in Côte d'Ivoire this year, we captured some mosquitoes and did some measurements with a biospace that we brought to the jungle. These have not been analyzed before, and the following results are from this specific mosquito that you see in these images. By the way, since we have a lot of knowledgeable people here, if anyone knows what species of mosquito this is, please let me know. We also have other mosquito specimens from this field campaign that we would gladly accept help in identifying. The proposed mosquito measurements you can do with biospace, I will go through, is optical cross-section in different directions, degree of linear polarization, and spectral analysis. With spectral analysis, we will also look into how we could find the wing thickness, the water content, and the melanin content in the mosquito. To evaluate the optical cross-section and how it's different in different directions, we spin the mosquito around. In this case, it's mounted so that we can evaluate the right and left side, the ventral and the dorsal side of the mosquito. To the right side, you see the polar plot of how the intensity is different. In this case, it's for 810 nanometer light in copol and dipole. You could mount it in a way so that we evaluate the anterior and posterior part of the mosquito instead. For finding the degree of linear polarization, you take an exposure with copolarized light and one with depolarized light. Then you can visualize it as a degree of linear polarization, where green corresponds to 100% copolarized light and red corresponds to 50%, thereby random polarization. As you can see on the left side of the image, the wings have a higher degree of linear polarization, which makes sense since they are a bit more glossy, and the body has a lower degree of linear polarization. You can easily evaluate the spectrum in different parts of the mosquito. In this case, I've selected the whole body and the whole wing, looking at the copolarized and depolarized light respectively. You can see a similar spectrum, but for the copolarized wing, we have a much stronger signal than for the other ones. So, why would we want to measure the optical cross-section, the degree of linear polarization, or the spectrum of these insects? Well, one reason could be that we have lidars which could probe the same kind of parameters, and by building a library of how these parameters vary for different insects, that could help us with identifying the different insects while doing these lidar experiments. Another reason would be to probe the physical quantities of the insect. Analyzing the spectrum, you can find the wing thickness through a phenomena called as thin film interference. This occurs when you have a thin film of a material with another refractive index than air, in this case chitin. Constructive and destructive interference produce the soap bubble colors seen in the mosquito wing below. How these interference pattern behave is dependent on the thickness of the wing, so by measuring the spectrum you can deduce the wing thickness. In practice, this is easier to accomplish with a high spectral resolution and probing the near-infrared and short-infrared region rather than a visible region. This means that biospace is not the optimal instrument for finding the wing thickness. Higher resolution spectrometers would be advised. It has, however, been accomplished with biospace for a bark beetle wing. Here we probe 3 different regions of the wing and fit the thin film equation, which is sampled by the 8 LEDs of biospace, to find the wing thickness of around 0.4 to 0.6 micrometers, which correspond to other literature. So it is possible in some cases, but with a low certainty. The equation found on this page describes this fringe pattern, and it's thoroughly explained in the paper Remote Nanoscopy with Infrared Elastic Hyperspectral LiDAR, which is published by our group this year. And in that paper, we evaluate wing thicknesses in free-flying insects with a higher spectral resolution and in shortwave infrared. Another physical quantity you could probe is the water and melanin contents. This has been done by our group, but note that this mosquito is not the same one we captured in Tai, and it's not measured with biospace. However, if you do have a spectrum into the shortwave infrared, you can fit a model of water absorption and melanin absorption, and from that deduce the water and melanin content of your insect. In this case, we try to see the differences of a 2-day-old mosquito and a 6-day-old mosquito. It's unfortunately not possible with biospace currently due to its spectral range ending before the water absorption at 1200 and 1450 nanometers, which is seen in this plot. The limitations of biospace can be addressed by an upcoming update, however. We have a new shortwave infrared version of the biospace where the light source have laser diodes ranging from 975 to 1640 nanometers. And to accommodate for the longer wavelengths, we have replaced the camera with an in-gas camera that has sensitivity to this new spectral range. With this update, we plan to do mosquito studies looking for the quantities I just mentioned, the wing thickness, the water and melanin content. One drawback of this new biospace is the price. The in-gas camera costs around 30,000 euros or 300,000 CDs. This concludes this presentation. If you're interested in any more details of these methods, please take a look at these papers. I'm also very happy to answer any of your questions. Thanks.